Okay, in today's video, I am going to show you how to calculate, how to determine the orbital velocity of an object that is orbiting another larger, more massive object. In this case, a satellite that is orbiting the Earth. Now, I'm not just going to give you the equation. I think it's an interesting activity, an interesting thing to do is to derive the equation for the orbital velocity to give us some idea about how the forces are working. Now, here we have the Earth. The Earth and the central object I like to designate as M1. Here's the object that's doing the orbiting, and I like to designate that as a lowercase m2. So capital M1 and lower m2. Now we know from Newton's law of universal gravitation that the force on M1 from M2 and the force on M2 from M1 are equal in magnitude but opposite in direction. So this force is equal to this force. Now, because this object is moving on a curved path, on a circular path, we like to designate that force as the centripetal force. It's the same force, it has the same magnitude, but we call it the centripetal force, and we can use Newton's second law to calculate the centripetal force. Newton's second law, of course, says the force equals the mass times the acceleration. The acceleration for an object that is moving on a curved path, on a circular path, the acceleration is equal to the velocity of the object squared divided by the radius of the curved path. Now we can combine these two equations and we can calculate the centripetal force by multiplying the mass of the object times taking the mass of the object, multiplying the square of the velocity, and then dividing it by the distance or the radius of the curved path upon which it is moving. So we know this is the centripetal force. This is the equation for the centripetal force. And then this force, of course, is Newton's law of universal gravitation, which says that g, the gravitational constant, times m1 times m2 divided by the square of the distance between the two objects is equal to the force. And we said earlier that this force and this force are equal to each other. These two forces are equal in magnitude but opposite in direction. So I can set those two equations equal to each other, and then we can solve for the velocity. Okay, and that's how we're going to get our orbital velocity. So I just took the equation for the centripetal force, the equation for Newton's law of universal gravitation, set them equal to each other. You'll notice we have an m2 on both sides. This value appears on both sides, so we can cancel those two. Also the radius, this radius and this radius are the same. Here we have one radius, here we have two radiuses, or radius squared, so I can cancel one of the r's on each of those, and we come up with that the velocity squared is equal to g, the gravitational constant, times m1, the mass of the central object, divided by the distance between those two objects. Now we don't want v squared, we want v, so we're going to take the square root. We get v is equal to the square root of g times m1 divided by r. This is the equation we use to calculate the orbital velocity of an object. Okay? Now I want to point out, because it's very interesting, that the mass of this object, the mass of the orbiting object, is not in the equation. That means the velocity is not dependent. The velocity of the object is not dependent on its mass. The velocity of the object is only dependent upon the mass of the central object and the distance that the object is away from the center of mass of that central object. Okay? For example, if we had another satellite that was the same distance away from Earth, but it had twice the mass, then the velocity would still be the same. The mass or the velocity is not dependent upon the mass. Okay? All right, now let's do an example. We have a communication satellite that's orbiting at a height above the Earth, altitude above the Earth of 781 kilometers. We want to know what is the orbital velocity. Well, we're just going to use our equation. G is the gravitational constant, 6.67. This is the mass of the Earth. The mass of Earth is 5.97 times 10 to the 24 kilograms. This r, as I said, is the distance that the object is away from the center of mass of the central object, or the center of mass of Earth in this case. Now we're told that the object is orbiting the Earth at a height of 781 kilometers. That's this distance, but we want to know the total distance from the center of mass to the object, from the center of the Earth to the object. So that means we need to know the radius of the Earth. The radius of the Earth is 6,371 kilometers. So this object is really the sum of these two distances away from the Earth. That's the way I think about it. It's really the way from the center of the mass, or the center of Earth. Okay? So now we're just going to plug our values in. The gravitational constant is 6.67 times 10 to the minus 11 Newton meter squared kilogram squared. The mass of the Earth we're given in kilograms, 5.97 times 10 to the 24 kilograms. Now the distance, I said we have to add these two together, but in addition to that we have to give the value in meters because the constant, the gravitational constant, is given in the units of Newton meters kilograms. Okay? So we're going to add these two together, convert into meters, and we get 7.152 times 10 to the 6th meters. Okay, if I add these two values together, I get 7,152. Then I converted it to meters, and I get 7.152 times 10 to the 6th meters. Not meters squared, just meters. Okay, you don't square the value. So that tells me that the velocity of that object is 7,462 meters per second. And I convert that into kilometers, and I get about 7.5 kilometers a second. All right. So an object that is orbiting the Earth at 781 kilometers above the surface of the Earth is going to have a velocity of just about 7.5 kilometers per second. And once again, I want to point out that that velocity is not dependent upon the mass. If I put a different object here with a different mass, the velocity will be the same because the velocity is not dependent upon the mass of the orbiting object. All right. Now another thing we like to do is determine the orbital period. How long does it take for that object to go once around the Earth? Okay. Now we're going to use the velocity equation, which says the velocity is equal to the distance divided by the time, or the speed is equal to the distance divided by the time. We want to solve for time, so I'm going to rearrange this equation, and I put capital T because capital T is the symbol we use for the period, and that's what we want to solve for. It's kind of a more specific time. It's the period. The period is equal to the distance that the object travels divided by the velocity. The distance that it travels is actually 2 pi r. That's the circumference of a circle. The circumference of a circle is 2 pi r. And that'll tell us, because it's moving a circular path, how far the object goes. Divide by the velocity, and we get the time it takes to go once around. You got to remember, 2 pi r, this is 2 times pi, times the radius. It's the total radius from the center to the object. And I left it in meters, because I'm going to get the answer in my velocity I'm using in meters per second. Okay? And then I'm going to divide that my velocity in meters per second. And I get that the time is 6,119 seconds. I can convert that to minutes. It's about 100 minutes. And I can convert that to hours. It's about 1.67 hours. Okay? So there you go. We did, I would say, 3 things. We derived the equation for the orbital velocity. We calculated the orbital velocity of an object, and we also calculated the orbital period, the time it takes to go once around the Earth. All right, I hope you found that video helpful. If you did, please do all the following 3 things. Subscribe to my channel, give me a nice thumbs up for this video, and also leave me a nice positive comment in the comment section below. Thank you very much for watching. We will see you in the next video.